Now, we do little bit more juggling with this coordinate transformation. So, let us do this. Let us now introduce two bases. When we said Q matrix, transformation from one basis to another basis. So, we have two bases, basis A defined by A 1, A 2, A 3 and basis B defined by B 1, B 2, B 3. Okay. And we defined a Q matrix, coordinate transformation matrix, which will transform any vector in the A basis to its component, it will transform its component in the A basis to its component in the B basis. That is what Q does. And we have decided to use these bases as the direct space where we are writing vectors as columns. So, these may be a direction vector as columns. So, the job of Q is to give you x b, y b, z b from x a, y a, z a, where x a, y a, z a and x b, y b, z b are components of the same vector, but referred to different coordinate system, different bases A and B, and Q is my transformation matrix which does this magic. Now, for every basis A, I can calculate its corresponding or determine its corresponding reciprocal basis. So, this is the reciprocal space. So, we are using it for example, for plane normals. Here the vectors, the common vector which we will be using is plane normal, and we will be writing them as row vectors. Similarly, for B there is a B star. Now, A can be related to the orthonormal basis. So, we have already two direct bases A and B which are talking through each other through Q. We have two reciprocal bases, corresponding reciprocal bases, who we want to know that in what language they are talking. So, their communication language will be some other matrix Q star, and we want to find out what is that Q star. In between there is an orthonormal basis which is a sort of communication hub which communicates through different matrices as you know. So, that we are calling them C. So, C A takes basis A to orthonormal basis, C B takes basis B to orthonormal basis. Similarly, C A star will take A star to orthonormal basis and C B star B star to orthonormal basis. So, Q, C A, C B, C A star, C B star and Q star. We have 6 matrices connecting these 5 different bases, and we want to find, the goal is to find Q star in terms of Q. What if we know the matrix which transforms direct space A to direct space B, what is the corresponding matrix Q star which connects reciprocal space A star to reciprocal space B star. So, let us do this exercise. let us write this q star. So, q star will help us to go from A star to B star. Now, suppose there is an obstacle, there is a landslide on that path. So, we will like to take a diversion. We first go to the orthonormal basis and then come back to B star. So, the net result of these two transformations should be same as the q star transformation, but what is going from A star to orthonormal doing? It is multiplying by C A star. And what will take us from orthonormal to B star? Yeah, C B star inverse. I am happy all of you are with me, C B star inverse. So, these two, the product of these two matrices should be same as q A star, because the end results are the same. Now, I can write C A star as, I know C A star is C A inverse and C B star is C B inverse. So, inverse of inverse is C B. So, we have C A inverse C B. We can write this as, again using the matrix inverse property, C B times C A whole inverse. Now, let us see what C B times C A will do for us. C A takes us to orthonormal basis and C B inverse. So, from A I come to orthonormal basis using C A, and then C B inverse takes me to basis B from the orthonormal basis. So, this is this path, which is equivalent to the net result is this path. So, I can write this simply as q, C B inverse C A is q, so q inverse. Yet another verification of the reciprocal space, name is fully justified. So, for any transformation, so what we had initially seen, that transformation to orthonormal, to a transformation to given orthonormal basis, C A star was inverse of C A for a given pair A and A star. Now, we are finding that even A was being taken to B to some other basis through Q, then A star will be taken to B star again by its inverse. Now, just a comment, not a new result. You have already derived that how will you transform. In fact, I can take a quiz now, that given Miller indices of a direction, how will you transform one Miller index with respect Miller indices with respect to one coordinate system to indices of the same direction with respect to another coordinate system. If I have UA, VA, WA as the Miller indices of one direction, then I just multiply it by that coordinate because it is a vector. Miller indices are nothing but what was UA, VA, WA representing? It was representing a direction UA times A plus VB times BA, sorry, VA times BA plus WA times CA. So, it is a vector and it is a vector in real space, and for real space is what we have set up Q for. So, we will get UB, VB, WB. And how will you transform the Miller index? So, this is for direction. How will you now transform a Miller indices of a plane? So, suppose I give you the Miller indices of a plane HKL. I give you HA, KA, LA. How will you get HB, KB, LB? Suppose we have a unit cell like this, A, B and C perpendicular to the plane of the paper. Then let us say 1 0 0 plane. One on the x axis, so it will cut the x axis here at A. 0 means infinite on the B axis, so it is parallel to the B axis. The plane should do something like this, and parallel to the C axis, so it is perpendicular to the plane of the paper. So, it is a plane like a prism face, it is standing on the plane of the paper perpendicular and is cutting the A axis at 1. This is what is 1 0 0 plane. But the 1 0 0 direction is a direction which is 1 A, 1 0 0 direction is 1 A plus 0 B plus 0 C. So, it is this direction, and you can clearly see that unless and until this angle, I did not say anything about this angle. Let us make it a hexagonal unit cell. So, this angle is 120 degree. So, if this angle is, so in hexagonal crystal a 1 0 0 direction is no more parallel to, or sorry, no more perpendicular to 1 0 0 plane. So, if you want that perpendicularity, that was, let us go back to our review, that is why that result is so important, do not take it lightly. So, this result needs to be now painted all red, but I do not have a red painting option. So, let me paint it all yellow. So, it is the G star, this star is very critical, not any arbitrary vector, but if you want in general for the HKL direction to be perpendicular to the HKL plane, the direction has to be in the reciprocal space, that is HKL have to be referred to A star, B star and C star. right. Now, we come back again to this exercise. So, now, so we can consider them as plane normals, but we should remember that we are in reciprocal space. So, that means we are transforming now not direct space vector, but reciprocal space vector, and we have established that relation, that how do we transform the reciprocal space vector? By q star or q inverse, only keeping in mind that we should write them as row vector. So, I should not write, I was deliberately writing it as column vector to challenge you. I should write it as row vector, and then I can happily transform them by q inverse. If you insist that my vectors are column vector, then you could have used q inverse transpose. So, if you say q inverse transpose here, then you are fine. So, either will give you the same numerical result, it is only algebraically writing style is different. Okay. Now, this fact, we have established this fact, that highlighted fact. Yeah. So, this equation or this relation, we have worked very hard to prove it. So, we can now much more easily prove that same relationship. So, let us try to do that. I am talking of proof of Weiss-Jones law. Weiss-Jones law, if you remember, Weiss-Jones law was H u plus k v plus L w is equal to 0 as a condition that you have a plane H k L, you have a plane H k L and you have a direction u v w. And we wanted to prove this. So, for this proof also means I got little diverted there. It is not regarding that perpendicular property, there also we used something like that, but for proving the Weiss-Jones law also we used something similar, that we constructed two vectors in the plane and then we showed that u v w is a combination of those two vectors. The u v w vector is a combination of those two vectors. But now, using our reciprocal magic wand, we can do much better. So, what is the vector normal to this plane? Yeah, vector normal to this plane G star H k L. And if G star H k L is normal, what will be its relation to u v w? So, G star H k L dot u v w is 0, but G star H k L is just a short form, we have just said it is short form of H a star plus k b star plus L c star, and u v w inside bracket is just a short form of u a plus v b plus w c, and this is 0. Now, this appears to be giving 9 terms, but you know the nice property of reciprocal space, that A star, only A star dot A will survive as 1, A star dot B is 0, A star dot C is 0. Similarly, B star dot A is 0, B star dot C is 0, C star dot A is 0, C star B is 0. That is the definition of the reciprocal lattice. So, this gives you then only H u A star dot A star K V, sorry, thank you, Anne, K V B star dot B plus L W C star dot C. Other terms are 0 and these terms also are just 1. So, H u plus K V plus L W is 0. Okay. One line proof for Weiss-Jones law. You can compare this proof with the previous proof which we gave, living totally in real space. Somebody was asking that day, why bother about reciprocal space in the first place? Why can't we do everything in real space? In fact, you can do everything in real space, because real space is real. This reciprocal space is in sort of imaginary construct, but the imaginary construct is to assist you in computation and assist you in many such simplifications. So, this is one example. You can prove Weiss-Jones law, everything is in, the quantities themselves are in real space. There is no need of reciprocal space here. HKL is a plane in real space, UVW is a direction in real space. So, the relationship is existing in real space, but a proof can be constructed, a simple proof can be constructed by lifting yourself up in the reciprocal space and then coming back again to real space.